Good afternoon, ladies and gentlemen. It is a pleasure and honor for me to be here and address a long-standing challenge in science, the capturing and controlling or steering the motion of electrons at the atomic scale. In my talk, I'd like to show you how attosecond physics and technology is now about to furnish us with this technical capability. The work that I'm going to present was done at the Max Planck Institute of Quantum Optics and at my chair at the Ludwig-Maximilians-Universitat of Munich. Both of them, in my case at least, are located at the northern campus of Munich, basically the campus Garching. What you see here, this is the Max Planck Institute, and this is our physics building accommodating 3 chairs, including my one. And by the way, just next to this building, which is not visible here because this picture is already a bit old, we are just building a 70 million euro laser center devoted to medical applications of ultra-short pulse high power lasers, mainly to research towards early detection and therapy of cancer. I would like to acknowledge a large number of co-workers, collaborators. I would not like to mention them by names, of course, at this point, but quite a few of them, the key collaborators and contributors, I'm going to mention in the context of results during my talk. Last but not least, I would like to thank Christian Hackenberger and WoogieWorks Animation Studio for the graphics and animations in my talk. What you see here is how the electric field of a few cycle ultra-short pulse laser field suppresses or is predicted to suppress the potential binding the electron or the hydrogen atom to the nucleus, which is obviously taking place on a very short time scale. Access to direct access to such electronic dynamics in space and in time requires a resolution of about 10 to the minus 8 centimeters and 10 to the minus 16 seconds, respectively. Correspondingly, direct human observation of such changes in space and time calls for magnification of about 10 to the 8 in space and 10 to the 16 in time. To warm you up for the subject of my talk, I would like to start attempting to bring to your mind how colossal magnification of 10 to the 16 is. Imagine you are sitting in a space station about 1,000 miles away from our planet, from where your unaided eye can hardly resolve structures smaller than the Italian peninsula, but with increasing zoom, ever finer structures become perceivable. Eventually in our direct environment, in this case in the beautiful city of Venice with its Piazza San Marco, where we can zoom in on a raindrop. To make this observable from outer space, we need a angular resolution of about 10 to the minus 8 radians, which is pretty exactly the same angular resolution being offered by the European Extreme Large Telescope, which is the biggest on Earth, currently under construction in Chile. So in order to make a raindrop visible from a distance of about 1,000 miles, you need a device that rivals in size an Egyptian pyramid. Of course, this pyramid is not standing in Chile. It's just shown here to provide you with the right scale. And even though already for this magnification you need such a big device, this is only half of the journey. Remember, I set out to demonstrate to you the magnification of 10 to the 16. So obviously we have to go on and continue this zoom into the interior of this raindrop, which guides us through the microscopic world of living creatures, small living creatures and large biological molecules, eventually down to the scale of atoms, down to the world of atoms and electrons. To make this atomic structure perceivable from outer space, we need a magnification of 10 to the 16, which we can achieve, in principle at least, by combining the space telescope presented before with a state-of-the-art electron microscope to actually make this magnifying power available. So basically, the combination of these two devices, of these two high technologies, could furnish us with a magnification of 10 to the 16 in space. By analogy, we can now do a similar journey in time, starting from our human time scale, best characterized by our heart beating approximately once per second, and then with increasing temporal zoom proceed to ever more rapidly evolving phenomena and processes and make ever finer details of their dynamics accessible to human observation. So at a magnification of about 10 to the 4, 10 to the 5, we can capture a bullet in flight. Actually, we can observe even how it is spinning during its flight. And if we move on and slow down time further, so increase the temporal zoom, at about 10 to the 9, 10 to the 10, we can capture electric currents being switched on and off billion times per second in microchips. At an application of about 10 to the 11, we enter the atomic world, where with increasing zoom we first freeze the motion of molecules as a whole, then the motion of atoms within the molecule on the femtosecond scale as shown here, and eventually on the attosecond scale also the motion of electrons represented here by their migration within biological molecules. So if you are asked what can be attosecond physics good for, you may choose to answer that it does the same job in time as a state-of-the-art telescope plus a state-of-the-art electron microscope are capable of doing jointly in space. Of course, this still doesn't answer the question, why on earth need we zoom in on an attosecond time scale? What kind of interesting things happen there that we may be interested in? Of course, there could be many answers to this question. My favorite ones are as follows. Actually, the first steps in the DNAs of our cells, of the cells that we are made up of, the first steps towards life-threatening diseases happen on this time scale. And an example from a completely different direction the attosecond time scale is also believed to be the ultimate frontier of electron-based signal processing, electron-based information technologies. So obviously, if one would like to approach this time scale, one would like to identify ways and technologies for getting closer and closer to these ultimate frontiers. One needs to have a corresponding metrology at hand with which the underlying physical phenomena, physical effects can be studied. And that's exactly what attosecond physics and technology furnishes us with. So just to wrap up this introductory part, kind of first take-home message of my talk: making the atomic scale motion of electrons accessible to human observation requires a temporal magnification of about 10 to the 16, and attosecond technology now not only furnishes us with this magnifying power, but as you will see in my talk, also with the capability of actually controlling, steering these motions on the atomic scale to an ever larger extent. So in my talk, I'm going to very briefly review the main tools in the toolbox of the current toolbox of attosecond technology, then their first and some of the more recent applications, kind of proof of principle experiments, which actually provide conclusive evidence for the metrology working well. Then I move on to latest advances, including improved capabilities towards not just observing electronic motion on the atomic scale in real time, but to increasing extent also controlling this. And last but not least, I would like to spend a couple of minutes at the end of my talk at looking a little bit into the future. So attosecond metrology's control are intertwined, both requiring a force acting upon the electrons to be steered and tracked that is variable in a controlled fashion on the relevant, that is attosecond time scale, and is also able to rival the forces acting on the electrons in atomic systems. All these conditions can be fulfilled by the electric field of few cycle laser pulses, provided that the waveform of these pulses is well controlled. These waveform controlled laser pulses became available back in 2003 as a result of a collaboration between my group and Theodor Hensch and Thomas Udem from Max Planck Institute of Quantum Optics, and opened the door to controlling and measuring electron processes on their natural time scale. So one of the perhaps most striking implication of this new capability is the generation and measurement of an isolated attosecond pulse. Let's first look at how we can generate these pulses. We focus such a few cycle linearly polarized laser pulse into an ensemble of atoms. Now we zoom in on such an atom, actually in our case neon atom, and watch how the probable distribution of electrons is modified, which is actually represented here by this green cloud. So as you see, as soon as the field becomes strong enough, at the peak of the first intense period in this pulse, the corresponding electric force may become strong enough to detach the most weakly bound electron with substantial probability via optical tunnel ionization. So as I showed you before, this strong field may suppress the Coulomb barrier and allow the electron to tunnel through this barrier. In the next moments, the field still points in the same direction and brings this electron away from the nucleus, but At approximately this point, the field direction is reversed. This accelerates the electron wave packet back to the vicinity of the atomic core, where its interference with the bound state portion of the very same electron results in charge oscillations, very rapid charge oscillations, and that forms a tiny antenna, and this antenna can radiate a burst of XUV or soft X-ray radiation. Here you see the result of a quantum mechanical simulations. You see how quantum mechanical interference between this returning wave packet, this is the movie is played back and forth. So here it is how the wave packet comes in, and the wave function of this wave packet overlaps with the wave function of that portion of the electron which remained in the ground state, and the result of this overlap, spatial and temporal overlap, is this oscillatory behavior and basically the formation of a corresponding antenna which radiates light. Since this wave packet overlaps in space and time with the bound state wave function only for a fraction of a femtosecond, that's at least what theory predicts, we expect the emission of a sub-femtosecond or attosecond burst. And the process, of course, happens in many atoms at the same time. And since our laser pulse is spatially perfectly coherent, these bursts emitted from the individual atoms are superimposed coherently, form a relatively intense XUV pulse that propagates collinearly with the laser beam used for its generation. The two beams are then guided into a second chamber. This whole game is being played in a vacuum system, because this extreme ultraviolet radiation otherwise would be absorbed in air. So we have to put these apparatus into vacuum. Both beams propagate to a second chamber where a two-component mirror focuses them onto some target. The internal part of this mirror focuses the XUV pulse, XUV beam, the outer part, the laser beam, and by moving the internal part with respect to the outer with a nanometer precision translation stage allows the control of the delay of one pulse with respect to the other with attosecond precision. This apparatus can be used for both characterizing, measuring the XUV pulse and the laser field on one hand, as well as after their characterization using these tools for attosecond spectroscopy, as I'm going to show you in the next few minutes. First, we need to characterize the tools. We need to know what kind of tools we have at hand before we can use them for any experiments. And in the next couple of minutes, I'd like to show you how we actually measure with this apparatus the pulse duration of the XUV pulse and the waveform of the fuse cycle laser pulse used for its generation. So to this end, we use a gas target in the common focus of the two beams and expose atoms, again neon atoms in our case, to the XUV pulse in the presence of the fuse cycle laser field. The electric field of this laser pulse is polarized towards a time of flight detector, where we analyze the final energy distribution, momentum distribution of the photoelectrons released by the XUV pulse. The photoelectrons released are accelerated or decelerated by this electric field of the laser pulse depending on their instant of release. This acceleration and deceleration imposes a change of their momentum that is proportional to the vector potential of the laser field at the instant of release, which is denoted by T here. So this relationship between momentum change and vector potential of the laser field is a simple result of integrating the Newton equation for this electron that has been kicked off by the XUV pulse. And what is important to note here, that within any half cycle of the strong linearly polarized laser field, this connection between momentum change of the electron and vector potential is monotonic. So the birth moment of the electron is unambiguously labeled by corresponding change of the momentum of the electron, or vice versa, the change in the electron momentum that we can measure by time of flight spectrometry is unambiguously labeled by the birth moment of the electron. This unambiguous and even monotonic relationship implies that the temporal structure of the XUV pulse releasing the photoelectrons is mapped to a corresponding momentum or energy distribution of the electrons, and this is what we can measure. And thanks to this monotonic relationship, we can unambiguously determine the temporal structure and the pulse duration of this XUV pulse. This actually, in this nice way, works particularly effectively if the XUV pulse fits within the half cycle of the laser field, but actually it can be shown that even if the XUV pulse is somewhat longer than the half cycle, it is still possible to completely retrieve the temporal structure of this XUV pulse from such a measurement. Imagine that, let's now imagine that this XUV pulse is actually substantially shorter than the half cycle of the laser field. In this case, the momentum shift caused would be more or less the same within the entire photoelectron wave packet released, and the only thing that happens is a shift up and down as the XUV pulse is scanned across the laser field. This concept has been dubbed light field-driven, optical field-driven streaking, with reference to the analogy of a streak camera. Its concept first proposed by Paul Corkum and put into practice by our group back in 2003, 2004, at that time still in Vienna. So the result of such a measurement, basically, if we record these XUV released photoelectrons, XUV released, XUV induced, and laser field streaked photoelectron spectra as a function of delay between the XUV pulse and the laser pulse, we typically end up seeing such a structure which actually directly displays the temporal evolution of the vector potential of the laser field. From the details of these photoelectron spectra, basically from the individual slices of the spectrogram, also the XUV pulse characteristics can be retrieved. In this particular case here, in a later experiment back in 2008, from this measurement we extracted a XUV pulse duration of about 80 attoseconds at photon energies of about 100 electron volt. attosecond metrology in its first incarnation, as I just presented it to you, arises from our capability of controlling the electric force of light and synchronizing processes under scrutiny to this force, both with attosecond precision, of course. In this first implementation of attosecond metrology, the XUV pulse served as a kind of starter gun, which initiated the process to be clocked by the controlled evolution of the electric field of the fuse cycle laser pulse. But we can also take a radically different approach by utilizing exactly the same tools. We can interchange their roles, and we can consider using the fuse cycle laser pulse for initiating and maybe even controlling some dynamics. Just think of some strong field interactions, which of course also sets electrons into motion, and use the XUV pulse for probing, for interrogating these dynamics. It is very reassuring that for this purpose we don't have to build new experimental apparatus, but exactly the same system that I've just presented you, which we have now used for measuring the XUV pulse and the fuse cycle laser field via attosecond streaking, can be easily turned to furnish it with the capability of implementing attosecond probe spectroscopy by simply delaying the XUV pulse with respect to the fuse cycle laser pulse and recording XUV-induced photoelectron spectra or the transmitted XUV spectra, photon spectra themselves as a function of delay between the fuse cycle laser excitation and the attosecond XUV probe. So this is the basic concept of attosecond probe spectroscopy. We can implement it either by recording transient absorption spectra or by recording transient photoelectron spectra. The first proof of principle experiment, we have opted for the first approach and addressed the question whether it is feasible to create coherent wave packet dynamics in an ion ensemble following tunneling ionization from quantum states of somewhat differing energy. To answer this question, we exposed krypton atoms to our strong fuse cycle laser pulse and released an electron from its most weakly bound filled shell, the 4p shell, which is composed of two different sublevels differing in energy by about 0.7 electron volt. This splitting is due to spin-orbit coupling. This difference in energy is much smaller than the binding energy of this state, which is close to 20 electron volt, and therefore we can release the electron from any of these two states with comparable probability. Thanks to this, after the ionization, we leave behind the ion in a kind of superposition state. And the question is that we try to answer now, to what extent this superposition state in the individual atoms is coherent to each other. A superposition state is always involving at least two wave function components. the wave function of this state and this state in this particular state. And the two components have to have a phase relationship with each other. And the question is, to what extent the phase of the two components is the same in the individual ions of the emerging ionic ensemble. We try to answer this question by probing the subsequent dynamics unfolding in this shell via attosecond transient absorption spectroscopy. We exposed the excited system, the ionizing system, to a delayed attosecond XUV pulse, which at a photon energy in the range of 70, 80 electron volts, which promoted electrons from the 3D shell to this vacancy created by the pump laser. And here you see the measured transient absorption spectrogram. So these are the individual spectra here as a function of delay between the ionizing fuse cycle laser field and the attosecond XUV probe. So it is quite obvious that these spectra exhibit very pronounced modulations with a modulation period of about 6 femtoseconds, which within this arrow bar here corresponds exactly to the inverse of this energy spacing of 0.7 electron volts. So obviously, we see here a clear coherence of the superposition state created, or in other words, obviously the resultant oscillatory motion of this electron, or perhaps more precisely whole wave packet, occurs in a highly synchronized fashion in the individual ions of the ensemble. This work was a collaborative effort together with the groups of Steve Leone from Berkeley and Robin Santra. He provided us theoretical support. Here you see the ensemble averaged probability distribution of the whole created in this in the krypton ions at different instants following the ionization. So the 0 femtosecond is the time instant which coincides with the peak of the ionizing fuse cycle laser field. That's what sets the motion going. And here you see how the ensemble averaged probable distribution of the whole created in krypton ion evolves. From these different snapshots, we can actually reconstruct the motion of this whole wave packet in the krypton ions in slow motion replay. This slow motion replay is has been done here with a time magnification of about 10 to the 15. So, during the first decade of attosecond science, isolated XUV pulses along with very broadband near octave bandwidth waveform controlled fuse cycle laser pulses have been applied primarily to simple systems, basically atoms in the gas phase. Now, with the technology at hand, well tried and tested, it's time to actually look into more sophisticated and less trivial dynamics. And in the remaining part of my talk, I'd like to show you how attosecond technology is now maturing to a point where it offers increasing possibilities for control by the generation of super octave light transients, and how we can actually extend the applications of these tools to increasingly more complex systems like molecules and in particularly to solids. And at the very end, I'd like to very briefly address how attosecond pulses with increased flux and in particular increased photon energy may become available by next generation femtosecond technology. So if we superimpose ultraviolet, visible and infrared light upon each other with adjustable phases and amplitudes, we can synthesize all sorts of funny and hopefully very useful waveforms. So we should be able to control the electric field evolution within the cycle, within the oscillation period of visible laser light, obviously on a sub-femtosecond or attosecond time scale, and can synthesize all sorts of signals similarly to standard microwave waveform synthesis, with the only difference that the time scale here is a few orders of magnitude shorter. To make such engineerable attosecond waveforms, attosecond light forces available for applications, we fed a supercontinuum extending from the near infrared down to the UV into a prototypical 1.5 octave 3-channel light field synthesizer, in which dichroic chirp mirrors subdivide this broad spectrum into 3 spectral channels of comparable bandwidth, into a near infrared channel, into a visible channel, and into a visible UV channel, which allows us to individually, separately manipulate these individual wave packets. We can compress them to their Fourier limit in these individual channels. We can chirp them if we wish. We can adjust their carrier envelope phase. And in particular, we can delay them with respect to each other. So if we wish to generate the shortest possible waveforms, we should better compress all the 3 wave packets. That's what we are usually doing. And what you see here is the variation of the resultant waveform by merely delaying these 3 Fourier limited wave packets with respect to each other. So you see, thanks to the super octave bandwidth, merely the delay, the temporal delay among these 3 wave packets already gives us a huge number of possibilities, furnishes us with a great deal of degrees of freedom to shape the electric field waveform on a sub-femtosecond to few femtosecond time scale. One of the most interesting ones, of course, is the shortest possible pulse, which at this bandwidth happens to be a kind of sub-cycle pulse. So more than 50% of the energy of this pulse is carried within one single half cycle of the laser pulse. Oh, by the way, this work has been led by Eleftherios Gouromakis. And let's now see how actually the electric field of such a subcycle pulse is predicted to ionize an atom. Here again the same animation as you already saw at the beginning of the talk, but now this is being done with a waveform that we have really synthesized. Here you see the instantaneous intensity of the same waveform, so just the square, the modulus square of the electric field. So you see indeed basically the central half cycle carries here a very large fraction of the total energy of the pulse. Eleftherios Gouromakis and his team traced this ionization process, this optical field induced tunnel ionization process again by attosecond transient absorption spectroscopy. And from the recorded transient absorption spectra, we could reproduce the degree of ionization as a function of delay between the probe and the ionizing field, and here you see the result. You see that the ionization seems to be confined essentially to the central half cycle to a time interval of about 700 attoseconds. Within this 700 attoseconds, 10%, roughly 10% of or maybe 9% of all the atoms is ionized. So it's really a very strong ionization. Nevertheless, a comparison with the well-known famous quasi-static theory, ADK theory, indicates that the ionization rate is a bit slower than predicted by quasi-static theory. This quasi-static theory means that you just use the same formula as derived for a static electric field, the same tunnel ionization formula, and allow this static electric field to vary in time. And if you just do this change in the formula resulted by this theory, you end up with such an evolution. So in this procedure, it is implicit that the electronic system, the tunneling rate, responds instantly without any delay to variations of the external field. Now you see that actually our measurement deviates from this prediction, which implies that already at this relatively slowly varying near-infrared field, it seems that the tunnel ionization process is non-adiabatic. It does not respond instantly to variations of the electric field, as obvious from this somewhat slower rate, which is certainly something the theory is supposed to address and come up with an explanation for. Equally interestingly, confinement of the ionization to one single half cycle allows the determination, the quantitative determination of its rate. In this particular case, we can evaluate from the slope of this ionization curve that we ionize 1% of the particles of the atoms within 100 attoseconds. So each 100 attosecond increases the ionization rate by 1% within this time interval. This capability is very helpful because this can provide actually a very nice quantitative test to modeling strong field ionization in complex systems where exact solution of the Schrödinger equation is not yet feasible, even with the biggest supercomputers, is not yet feasible. So obviously, theorists need to do some simplification and come up with some simplified models. And of course, then the first thing is always to validate this model, and for that, such a quantitative measurement can be very helpful. So attosecond resolution is not only required for electron phenomena in atoms, but there is a huge number and range of electron processes in solids that also evolve on this time scale, including quite a few ones that are highly relevant to advancing electronics to its ultimate limits, such as angstrom scale charge transport and the optical field-induced changes of electronic processes. Attosecond streaking turns out to be ideally suited for studying electron transport on the angstrom scale in real time. To this end, we shine in an XUV attosecond pulse with which we kick off electrons from some core levels in a solid. And obviously, if we do so simultaneously from different energy levels, then the electrons released from these quantum states of different binding energy will propagate at a different velocity and will arrive at the surface of the solid at different instants. This arrival time difference directly shows up or manifests itself directly in a corresponding shift of the attosecond streaking spectrograms recorded simultaneously on the low energy and the high energy electron. The first measurement of this kind was performed by Adrian Cavalieri in collaboration with, of course, quite a few members, other members from my group, Reinhard Kimberger, Ulf Kleineberg, and in particular also with collaborators from other groups. Pedro Echenique supported us theoretically and Ulrich Heinzmann experimentally. So in this first measurement, we measured an arrival time difference of about 100 attoseconds between electrons originating from the 4F core shell and of the conduction band of tungsten. Subsequent studies guided by Reinhard Kimberger brought to light that these propagation times are extremely sensitive to both the excitation photon energy, the XUV photon energy, as well as the system choice. For example, let's just look at these examples here. The photon energy, the excitation photon energy was changed from 105 to 120 eV. It's not a huge change. And the propagation time difference between the 4F electron and the conduction band electron changed in tungsten, changed from 100 attosecond down to about 30 attosecond. So from this, it's obvious that in the two cases, the effective mass of the electron must be very, very substantially different. So we may conclude from these measurements that attosecond electron propagation chronoscopy appears to be a very sensitive probe of high energy band structure in solids. Here is Reinhard and his co-workers involved in this study. He and his team then went on to use this powerful technique to study electron transport through artificially produced layers put on the surface of some substrate, in this particular case tungsten. And again, the 4F core electrons from tungsten have been referenced, the propagation time through individual magnesium layers on top of this tungsten substrate has been referenced to 2p electrons released from the magnesium layers themselves. And here you see the result of this study, basically the propagation time through these layers as a function of the number of magnesium layers. It is obviously increasing monotonically and nearly linearly with the number of layers. And of course, you could immediately say, well, that's quite trivial, and there's nothing surprising here or nothing even new or some valuable information. And you might perhaps at first sight be right, but only at first sight. It turns out that these seemingly trivial results bring to light something highly non-trivial. Remember, what determines this propagation time is the arrival of the electron at the surface. Why at the surface? Because it is at the surface where actually the electric field starts acting upon these electrons and start doing the streaking measurement from which we extract this time delay. So apparently, if this electric field would penetrate a little bit into this material, then we would not measure here the arrival time to the surface, but the arrival time at the point where this electric field of the streaking laser starts acting upon the electrons. So far we just tacitly assumed that there is a perfect screening on the surface of this material, and the normal component of the electric field, what matters for the streaking, indeed is abruptly suppressed within the material. So if you just take the Frenner formula, then for magnesium, you will find that this normal component of the field drops to just a few percent of its value above the surface, if you go below the surface. So now the question is, does this screening of an optical field on the surface of a metal really occur abruptly? Obviously, if we look at this microscopically, the answer must be no, nothing happens abruptly on a microscopic scale. There must be a finite screening depth, and we have now the metrology at hand with which we can answer for the first time what actually is this finite screening length. So how do we do this? We just take a simple phenomenological model in which we allow the electric field to be screened over a finite depth, which we denote by delta, and we do calculations with this model. Here you see the results for different screening depth, and all we have to do is just to compare the results of this simple model with the experiments. Obviously, these here do not fit, so we can now gradually eliminate those curves which obviously are not reconcilable with the experimental results, and leave only those which at least barely can be reconciled. And the most extreme one is this red one here, calculated for screening depth of 2.6 angstrom, but as you actually can see, even this is already pretty far off thanks to the quite good accuracy of these data points here. So probably the screening depth is even significantly less than this 2.6 angstrom, but in any case, we certainly can safely conclude that from these measurements that the normal component of an optical field is screened within less than one atomic layer on the surface of a metal, in this case magnesium. Seeking answer to the fundamental question whether physical properties of solids can be substantially modified by the instantaneous field of light, Martin Schulze and co-workers exposed a thin sheet of fused silica to a fused cycle laser pulse at intensity levels very close to damage threshold to probe transient changes induced by this very strong field, transient changes in both band structure and, if it happens, in conduction band population. The methodology again was transient absorption spectroscopy. To this end, a time-delayed XUV pulse with a photon energy corresponding to the energy difference between the L shell of silicon and the conduction band of fused silica, corresponding to about 100-110 electron volts, was used. And these XUV photons promoted electrons from the L shell of silicon into the conduction band and basically probed changes in band structure and possibly in population of this conduction band. Here you see the change in optical density at the absorption edge, basically at the edge of this conduction band. It is very conspicuous that this change in optical density, this is a negative change actually. The optical density gets smaller up here from 2.7 to 2.6. So we observe a near instantaneous change in the optical density that is obviously fully reversible. So after the few cycle laser pulse, this change is actually restored, and the system returns to its equilibrium state, as far as we can tell it within our error bars. And equally interestingly, these changes exhibit oscillations in complete synchrony with the oscillating electric field. So from these findings, it is obvious that these changes are driven by the instantaneous field, and that these changes must be dominated by dynamic changes in the band structure, rather than population transfer. As a matter of fact, any real population that would be promoted from the valence band to the conduction band by the strong field would survive there for at least a picosecond after the excitation. So if this population would provide a significant contribution to these variations in the optical density, then we would end up having here a high value, a high change also after the laser pulse passed the sample, which doesn't seem to be the case. This work was theoretically supported by Vadim Apalkov and Mark Stockmann, and they actually predicted that the strong field-induced transformations in band structure that are responsible for these reversible field-induced changes in optical density are likely to substantially increase the conductivity of the sample, basically the AC conductivity. If so, we should be able to generate an electric current, and to this end, we sent in a second weaker laser field and deposited two electrodes on the surface of our fused silica sample, and indeed were able to measure a current induced by this weak control field. Here you see this current as a function of delay between the strong pump pulse, which transforms the material from an insulating state into a semiconducting state, if you wish, or a reasonably strongly conducting state. And the control field actually drives the generated or the injected free carriers to the electrodes and induces the current in this external circuit, which we measure here. Each time the weak control field is delayed with respect to the strong pump field, we see a change in the sign of the current, as you see here. And the same happens at any fixed delay if the direction of the control pulse is flipped by just shifting its carrier envelope phase by pi. So these findings provide clear evidence that it is the instantaneous electric field that drives this current and indicate the feasibility of turning an insulator into a conductor largely reversibly and using it for switching current at light frequencies. This effect could meanwhile be used for ultrafast metrology, and the first application of attosecond solid state metrology has been a compact light phase detector, which relies on the dependence of this current on the carrier envelope phase of the laser field driving this current. We have calibrated this dependence by a gas phase experiment where The physics is very, very clear, and there is no doubt that we are able to model the process. And with that calibration in place, we can determine the carrier envelope phase by just reading the current. So I hope I've been able to convince you that attosecond physics may not only be helpful in providing us real-time access to microscopic dynamics, but possibly also instrumental in advancing signal processing and in particularly ultra-fast metrology to petahertz frequencies. If I get maybe 2 or 3 more minutes, then I would like to conclude my talks with a brief look into the future. And I'd like to start this by pointing out that all the experiments that I've presented so far have been based on titanium sapphire ultrafast laser technology, providing peak and average powers on the order of up to a terawatt and several watts, respectively. So, of course, you can produce with TiSafe lasers much more intense pulses at many, many terawatts, even beyond the petawatt frontier, but at very, very low repetition rates. That's not really useful for this type of metrology. Here, we really need repetition frequencies in the range of kilohertz or more. And in that range, unfortunately, the peak power of titanium sapphire laser systems can not dramatically exceed the terawatt level. It is quite obvious that further advances of attosecond technology demands few cycle light with orders of magnitude higher peak and average power, and it is also quite obvious that this will not be feasible with titanium sapphire based laser technology. Fortunately, the solution is on the horizon. Broadband optical chirp pulse parametric amplification driven by multimillijoule kilowatt scale sub-picosecond ytterbium YAG disc lasers have already demonstrated the capability of going way beyond what titanium sapphire based technology offers. We at Munich are currently in the process of actually developing a third generation femtosecond system with these parameters here: pulse duration near 1 femtosecond, pulse energy 50 millijoule, peak power 30 terawatts, average power 250 watts. It's obvious that this vastly outperforms titanium sapphire technology, and we even believe that a few years later this technology can also be scaled towards hundreds of terawatts peak power. This will allow the synthesis of multi-octave, multi-terawatt light transients. I deliberately don't refer to these guys here as light pulses anymore, but rather light transients, to emphasize the fact that here we cannot think of these pulses in terms of the carrier envelope decomposition of the pulse anymore, but you really need to think of them in terms of their real electric field, which varies very, very strongly and pronouncedly within the optical cycle of the carrier frequency of these transients. With the system that is currently under development in Munich and which hopefully will be commissioned within a couple of years from now, with these parameters, we have been able to predict that it should be possible to extend attosecond pulse generation to the photon energy range of 2.5 kilovolts. And if we just take a few hundred electron volts fraction of this spectrum here, we end up with 5 angstrom scale isolated attosecond pulses with a duration in the range of a few attoseconds. Obviously, this would be the ideal tool for imaging atomic scale electronic dynamics by X-ray diffraction, by time-resolved X-ray diffraction, with the necessary time and spatial resolution at the same time, so time resolution in the attosecond regime and spatial resolution in the picosecond regime. So with this, I would like to conclude. These synthesized multi-octave optical fields and attosecond, I should say, soft X-ray pulses for this community, hold promise for observing in real time virtually all motions, including electronic and structural in complex systems, including biological molecules and condensed matter, and exploring the ultimate speed limit of signal metrology and processing, as well as identifying viable routes to approaching this limit. Thank you very much for your attention.
Thank you for that great talk. I'm sure you'd be willing to take some questions, sure. If there are any in the audience.
Well, thank you for this very impressive set of accomplishments, quite exciting. What I was wondering was the examples you gave were individual atomic events where there are no coherence between the electrons, but electrons in solids are also correlated. So are there possibilities to look into the correlated effects in electrons rather than individual fluorescence-like or atomic-like excitations?
Thank you very much. A very good question. Yes, we believe there is. Of course, here in the first place, theory is challenged and is expected to identify routes to actually interrogating electron correlations. There have been quite a few papers on how attosecond pump probe spectroscopy could provide access to electron correlation, very simple two electron systems in helium, where one attosecond pulse could kick off the one electron of the helium atom, and another one, and the pump and the probe pulse could watch how the second electron that remains within the atom actually responds to this, and what kind of dynamics occur there. So there are attempts to actually look into this, but I'm not aware of any theoretical studies on solids yet. So this obviously one of the next frontiers, but it is quite obvious that electron correlation in solids, for instance, screening of a hole, if just in the simplest possible process we can think of, let's ionize an electron from a core shell in a metal. You create a point-like positive charge there, which obviously is almost instantly screened by the free electrons of the metal, and it's quite obvious that this screening happens on a very, very fast, most probably sub-femtosecond scale. This is just one example, but there is certainly many other examples for this, and yes, I think this is going to be one of the most exciting new frontiers to look into electron correlations.
So what you showed is that basically you can do with visible light what one used to be able to do with microwaves. So you can just control the electric field amplitude, and basically you take your catalog components and build your microwave circuit, or in this case light circuit. So let me ask in a different direction about quantum optics. Can you control, for example, the number of XUV or deep UV attosecond pulse photons you're getting out of there? So you showed this process where I think each of these krypton atoms in there would generate exactly one XUV photon, because I mean it's one electron wave packet that returns and then knocks off one photon. And if you can do that, then can you create non-classical states of light where you have, like a Fock state, for example, an exactly defined number of photons? And to go even further, perhaps even entangled states where you have these high noon states where exactly n photons are on one side or exactly n in the other.
Very, very good point. Thank you for the question. So, of course, this is also a very, very obvious thing to think of to actually extend the capabilities we have developed in the optical regime for shaping the intensity of light, the chirp of light, into the XUV regime, into the attosecond regime. Now remember, the generation of these attosecond bursts take place within one optical cycle. On the peak of a half cycle, the first intense half cycle, we detach the electron from the atom, as I showed in my animation. And within the very same optical cycle, the electron returns, recollides, recombines into its original ground state with some probability and emits an XUV photon. So the whole generation process from the release of the electron via tunnel ionization and the release of the XUV pulse via recombination of the liberated electron occurs within one laser cycle. What is the obvious implication of this? If we wish to control this process, we need to be able to shape the temporal evolution of the electric field that controls this whole process within the laser cycle. We need to be able to modify the waveform within the laser cycle. What do we need for that? Bandwidth, bandwidth, and bandwidth. We start being able to do this at bandwidth exceeding 1 octave. If we have 2 octaves, we have more degrees of freedom. If we have 3 octaves, even better. Then we can start doing this, what I'm showing here. Basically, you see here, thanks for the question. For my next talk, I will indicate here actually the time period corresponding to the period of the carrier cycle, which is about 3 femtoseconds here. Within these 3 femtoseconds, here you see a lot of structures, different structures depending on how we synthesize this wave. So obviously here we have already enough bandwidth to actually shape the driving field, the field driving this attosecond pulse generation process during the process of the emission of this pulse. So obviously this is the key tool to shaping the attosecond pulses. And I think this is going to be an other frontier in the next few years. Thank you for the question.
Any other questions?
In the case of Krypton, where you have the superposition of the two core states, do you also have double core excitations? Do you have to worry about that?
We would like to worry about that, but I guess this is much less probable. So it would be interesting to look into that as well, but probably we need much higher intensity for that. It would be interesting to look at this, definitely.
Okay. Well, let's thank our speaker one more time for a very
Thank you very much.
talk.